Right. So this is, I've written it as a carry ripple adder. The ripple here means that the carry out which is being generated from the individual bit full adder circuit is kind of propagated or rippled to the next bit addition. So here it's a very simple example of 4-bit addition. So what it really means is if I have a 4-bit of A4 to A1, where 1 is the LSB bit and 4 is the MSB bit, and I need to add it with that of the B input, again a 4-bit input, then the addition should give us the sum of 4 bits with a carry out expression, right? The A4 before, and then there will be a carry out, and this addition or this particular adder circuit should also be able to incorporate the C input, right? Or also the C output, or also called as the C input to this particular 4-bit addition. Right, so once we understand this we can easily scale it up to any higher order adder bits. So here, at an individual level, at a bitwise level, it is the first bit getting, it's a full adder representation of the first bit. The second bit full adder representation. So similarly, the third bit and then the fourth bit full adder representation. The sum is written here as S1, S2, S3, S4, and then finally the carry out of the A4, B4 addition will give us the C4 addition, which is nothing, the C4 carry out, which is nothing but the carry out of all the 4-bit adder, right? And this also incorporates the carry input. The C0 can also be written as C input to this particular 4-bit adders system. And this particular C0 and then A1 and B1 should be able to define what is the S1. So the S1 is defined as the A1 XOR B1 XOR C0. And the C1, which is generated, which is the carry generated by this first bit of addition, is then supplied to the second bit of addition. And then similarly, C2, which is generated, is supplied to the third bit. C3, which is generated, is supplied to the fourth bit addition. And then similarly, we'll get the C4 as the carry out of the 4-bit addition. The C1 here is nothing but the majority gate of, it is defined as a majority gate of A1, B1 and C0. And so that's what is written here, A1, B1 plus A1, C1 plus B1, C0. Right, hope this is clear. Now, if I want to find out, the 16-bit adder, right, this 16-bit adder is going to generate a C16 supplied with A1, B1, A1, C0, or rather A1, B1, C0. And similarly A2, B2, C1, and then similarly A16, B16, right? So for a 16-bit adder system, we'll be able to generate the sum 16, or rather the sum S1 to S16, the carry out C16. The inputs that have been provided is A1, B1 to A16, B16, and then there will be a C0, that is the carry input to that particular 16-bit addition, right? So these are the inputs. And then the outputs are S16, S1 to S16, and then the carry output of represented as C16. The question is, what should be the delay for this 16-bit carry ripple adder circuit? So let's take a look at it one by one. So let's also assume that all the inputs are available at time t is equal to 0, right? So all the inputs, that means A1, B1, to A16, B16, all of them are available at time t is equal to 0. C0 is also available at time t is equal to 0. Right? So to generate this C1, right, this C1, if I want to generate, which is nothing but the majority gate of this A1, B1 and C0, it is written as the A1, B1 plus A1, C0 plus B1, C0. That means when A1, B1 are available easily, A1 and C0 are also available at t is equal to 0, and B1 and C0 are also available at t is equal to 0. A1, B1 is also available at t is equal to 0. So if I actually put it into an 2-input AND gate here, so I will be able to get the output of A1, B1. AND gate parallel, one more 2-input AND gate, I'll get A1, C0. One more 2-input AND gate will get the output of B1, C0. So all these outputs, I can give it to a 3-input OR gate, and then that is going to generate the C1 bit, right? So the C1 bit will take a delay of 2-input AND gate and then the 3-input OR gate, assuming that I will have 3 of the 2-input AND gates which will be generating the outputs simultaneously. and then that will be fed into the 3 input OR gate, and then the output will be nothing but the C1. Once I have C1, the C1 is then passed to the generating the C2 as well as passed to generating the S2. All right. So now I have utilized the delay of 2 input AND gate and then a 3 input OR gate. Right. So the C1 is then fed to the A2 C1 and then B2 C1. Notice that A2 B2 A16 B16. In fact, all this what I have actually annotated with the bounding box here. A1 B1 A2 B2 A16 B16 can be actually be generated because all of the inputs are available at time t is equal to 0. So this will be generated if I have a lot of parallel 2 input AND gates. Then all this outputs of A16 B16 A15 B15 A2 B2 and A1 B1 will be generated at the same time, right? That will be the delay of 2 input AND gate. So the output of this A2 B2 is actually waiting for at the input of the 3 input OR gate, but it is waiting for A2 C1 to be generated and B2 C1 to be generated. But C1 is generated only when we have the output of this 3 input OR gate, right? So the moment C1 comes in, it gets into the AND gate. The output of this AND gate and this particular AND gate will be fed into the 3 input OR gate, and then it generates the C2, right? Which will be got here to generate to S3 the sum 3 bit. And similarly, it will go here to generate the C3 bit, and then similarly C15, and then similarly C16, right? So the overall, the delay from C0 to C16 is actually limited, or it's actually depends on the previous carry output bit, right? So what it means is if I want to generate the C16, then it has to depend on the time or the propagation delay for the C15 bit. Before that, C15 has to depend on C14, C14 has to depend on C13, and then so on, right? C2 has to depend on C1. So overall, if I look into this particular, the carry ripple adder, which is generating the carry output, for generating the C0 to C16, for generating the C16 output, it will take OR gate expression. So it will take the OR expression. So it is nothing but the 3-bit OR gate, 3-bit OR gate, right? 3-bit OR gate, 3-bit OR gate, and that will be the 3-bit OR gate is generating the C1, the 3-bit OR gate is generating C2, 3-bit OR gate is generating C15, C16, and so on. So it depends on the 3-bit OR gate here, as well as the delay also depends on the AND gate here, right? The moment C1 is available, then it has to wait for the A2 C1 to be output to be generated, B2 C1 output to be generated, and that is fed into the OR gate to generate this the C2 expression, right? So for a C2 to generate the C2 here, right, it has to wait for this OR gate. It has to wait for the 2 input AND gate here. The output of that will be fed to a 3-bit OR gate, and then that will be fed into a 2-bit AND gate, and then that will be fed into the 3-bit OR gate. So even for a C2, it has to, the overall delay will be twice the 3-bit OR gate plus the 2 AND gate. So similarly for C16, it is 16 times 3-bit OR gate plus 2-bit AND gate, right? Now, whereas for a sum expression, A1 B1 C0 to A16 B16 all are available here at time t is equal to 0. So the XOR operation of A1 B1 A2 B2 A15 B15 A16 B16, and the output of it is already available, right? And it is kind of delimited. So the S16 is kind of delimited because delimited by the C15. Whenever the C15 is available, it will do an XOR operation and then get the output, because A16 to XOR B16 output is already available, have already reached, and it just waits for the C15 to be available. Similarly, S15 will wait for C14 because A15 B15 is already the XOR operation is already done, assuming that all these XOR gates are in parallel, are parallelly made available, and A1 B1 to A16 B16, the inputs are already arrived at t is equal to 0. Right. So with that particular condition, what should be the delay for to generate the S16 bit starting from C0, right? What should be the S16 bit output that is being generated? How much time or the delay it takes, right? So the delay it takes is nothing but to generate C15 and then one more XOR operation, because this is already done, So this particular bounded box I have indicated here, saying that this is already the moment A1 B1 all of them are available at t is equal to 0. One 2-bit XOR gate will be generating all this outputs of A1 B1, A2 B2, A16 B16, right? So then it just have to wait for the C15 output. Once the C15 output is available, then it does an XOR operation, and then we will get S16 output. Right, so C15 will be available for for when this is generated. So this is generated, it has to wait for 15 times the T3-bit OR gate plus T of 2-bit AND gate. Right, so if it is C15, it has to be 15 times T OR gate plus T AND gate. Right, so 15 T OR plus T AND, and then one one T XOR delay will be able to give us the delay for the generating S16 bit. So 1 T XOR means 2-bit XOR gate, whatever is the delay, that is this particular XOR gate. Right, once C15 is available, then it will XOR with the output of A16, B16 XOR, right, and then give us, so this is my XOR output here, and C15 whatever time it takes, so this is this 15 into T OR plus T AND. So if I look into this, the delay can be actually be expressed in terms of AND and OR gate for generating the C16 bit or whatever the carry output bit, and for the sum bit it is nothing but 1 XOR and then the 15 T OR and AND gate. So this 15, instead of 15, we can also say that for an n bit addition it will be n minus 1 AND OR gate, and then that of plus the delay of the XOR gate. Right, so let's have a look at the generate and then the propagate signals here. So this is the truth table which we have anyways seen this earlier, right? So this particular truth table is anyways seen earlier, and then I had also made a very brief definitions of the propagate and generate signal. But once again, we will have a look into it, because then we will be able to use this for designing the adder subsystem blocks for the higher order adder bits. Right, so the generate and propagate signal, for the generate signal, the definition is A and B, the inputs A and B, right, will be truly generating this carry output independent of the C input. Right, so that is possible only when the carry output is 1 and when A and B, both of them are 1. Right. And irrespective of the C input being 1 or 0, it actually generates a carry out. Right. So independent of the C input, if it can actually, if it generates a carry output signal, then the generate signal is 1. So that's what the definition says. And that is possible only when A and B are, both of them are 1. All right. Propagate signal, it has been said that if it is 1 when the carry out logic is when the carry out is 1 and the carry input is actually 1, and that is possible only in this case, right? The carry output is 1, so the carry input is kind of propagated to 1 and carry input is propagated to carry output as 1, and so if I look into the proper definition, so the propagate P, so it carries if its carry out is true when there is a carry input, right? So going back, so the carry output is 1 when only when there is a carry input, right? And in this particular case, it actually generates a 1 here, but this 1 is actually generated by A and B, right? And then not by this carry out. Right, because here carry out is 0 and still it is generating 1, right? Whereas here in this particular portion of the combination here, the carry out, whatever is the carry carry input, it is kind of propagated here. Even if it is 0, it is actually propagated to 0 as in the carry out. So that is possible only when with respect to the A and B inputs, it is possible only when A and B, one of them is 1. So the propagate signal is actually an XOR operation of AI, BI or whatever. In this case, if it is the first bit, I can write it as A1 XOR B1, or if it's an ith bit, it is AI XOR BI. The generate here, if with respect to the definition of A and B inputs, so the generate bit will be nothing but the AND operations of AI, BI. So that's what I have mentioned here in the next slide. So the generate is the AND operation of AI BI. The propagate is the XOR operation of AI BI. So what it really means is, if PI is 1, that is only when the carry out is kind of propagated from the carry input. Right? GI is 1, that means the ith bit is actually generating a carry out. Right? So with this particular definition, what we know is the sum bit can be expressed as A XOR B XOR C input. And then the C input can also be considered as Ci minus 1. And this sum I can also state it as Si for the ith bit, Ci minus 1, the carry input, AI, Bi expression. So AI and Bi, I can consider it to be nothing but the Pi, the propagate bit. So the propagate bit XOR with that of the Ci minus 1 will give me the sum bit. So that is how we will be using this bitwise propagate signal to define our the sum output and also to that of the carry output. Right. So what we have seen so far is we defined the Pi bit, the propagate bit here. We have defined the GI bit here, the generate bitwise generate and then bitwise propagate signal. This we are going to use it to define our sum expression, to define our carry out expression, right? So the carry out will be nothing but Ci for an ith bit. The sum for the ith bit is sum Si. Carry input is nothing but Ci minus 1. Right, so we'll use this particular definition to redefine our sum expression and then the carry output expression, and try to visualize the different adder circuits. Right, so here is a definition of a group-wise generate signal. So until now, what we had seen is the bitwise GI, right, which is nothing but AI and BI. But here it is defining a group-wise generate signal of I minus 1 is to 0. So what it really means is, if I am using an adder circuit of, let's say the 4-bit adder circuit, right? So for a 4-bit adder circuit, I can actually generate a group-wise, right, 3 is to 0, right? So a group-wise generate signal 3 is to 0, right, and then use this for my to express the 4-bit addition sum expression and then the carry out expression, right? So what I'm saying here is the definition of the group wise I is to j and pi is to j still remains the same. So gi is to j and pi is to j. So this is a group wise now. So ij are not an individual bits. I and j are not same. It is, a different numbers. So let's say that I can take an example of 3 is to 1 or p of 3 is to 1. So this becomes 3, 2 and 1 bit, 3, 2 and 1 bit. So the definition still remains the same, saying that generating the carry out from the group irrespective of the carry input to the group. Right, so generating the carry out from the group irrespective of the carry input to the group will have my generate signal as 1. Right, so if I have a block of 3 bits and this is my C input to that particular 3 bits, right, and then this is the output of that particular 3 bits. The definition says if the C output is truly independent of that of C input, so irrespective of the C input, if it is generating C output, then we can say that this G3 is to 1 is actually 1. Similarly, propagate signal, it is the definition still remains the same. The propagating a carry out from the group when there is a carry input to the group. So similarly, if the C input here is 1 and then C output is kind of this C input is propagated to the C output, we can say that the propagate 3 is to 1 is actually 1. All right. So this is the group-wise definition of generate and then the propagate signals. And this particular, the group-wise generating signal of Gi minus 1 is to 0 is nothing but the carry input, right, for the ith bit. So what it also means is if I can actually generate the group wise I minus 1 bit, I minus 1 is to 0 group wise generate signal, that is nothing but the carry output of I minus 1 bit for the group I minus 1. Right, so gi minus 1 is gi minus 1 to 0, that is the group generate signal, is equal to the carry output of I minus 1 bits, right, I minus 1 to 1 bit. Right, so this is the carry output, so it will also act as a carry input to the ith bit addition. So this is what the group wise generate signal is kind of defined. Now let's take a look at it, whether it really makes any sense here. So if I consider G1 is to 0, by definition, the group wise generate a signal, it says, G1 is to 0 is nothing but 1 is to 1 plus P1 is to 1, and then G0 is to 0. G0 is to 0 is nothing but G0, P1 is to 1 is nothing but P1, and G1 is to 1 is nothing but G1. So what it means is, if I have the same I and J as same, it is nothing but it dissolves into a 1 bit. It generate bit level generate signal and bit level propagate signal, right? And then the bit level generate signal. So G0, P1, G1, that is what is G1 is to 0. G1 is nothing but A1, B1 AND gate. P1 is nothing but XOR gate of A1, B1. And G0 is nothing but C0, the carry input to the first bit addition, or we can say that the carry output of the 0th bit addition. All right. So if I actually resolve this or try to express this in terms of G1 is to 0 is what? So I'll actually use this, try to solve this expression. So A1, B1. So I'll take this expression, this one and then this one together. So it will become A1 common and B1 plus B1 bar, B1 and B1 bar, and then C0. So I'll take this particular expression and this particular expression to be common, plus A1 bar, B1, C0. So I'll get this particular expression. Moving ahead, so this particular expression, I'll take this B1 to be common. So I will have A1 plus A1 bar C0 plus A1 A1 here, and then so this one, I think I've taken this one and then this one together. So I'll get this to be here, and then finally B1 into A1 plus B1 into C0. So this and this will be nothing but B1 into A1 plus B1 into C0 plus A1 into C0, which is actually nothing but the majority gate, or rather nothing but the C output of the first expression. So that will be nothing but C1, right, of the first bit addition, right, or whatever it is, C output for the first bit addition. So G1 is to 0, or rather the group generated, the group generating signal for 1 is to 0 is nothing but C1. Similarly, if I do the expression G2 is to 0, turns out to be nothing but the carry 2, right? So the sum expression, I can actually write it in terms of the group generating signal. So if I want the sum, if I want the sum 1 or sum 2 here, once the C1 is generated, we know that it will be nothing but A2 XOR B2 XOR C1, right? Which I can also rewrite it as A2 XOR B2 XOR G1 is to 0 in terms of the group generating signal. And A2 and B2, I can actually write it in terms of the propagate bit level propagate signal P2 XOR with that of G1 is to 0. So similarly, I can actually write C ith bit is nothing but the XOR operation of the propagate bit level propagate signal Pi, and with that of the Gi minus 1 is to 0. All right. So if I'm generating the sum of the ith bit, it is nothing but the propagate of the ith bit XOR with that of the group generate of the previous one. So the I minus 1 with respect to 0. Right, hope this is clear. So this is the overall a broader definition of the group generate signal starting from I is to j. So starting from I is to j, I can redefine this as G I is to k plus P I is to k, and then G of k minus 1 is to j. So this is P I is to k is a group propagate signal. This is a group generate signal. This is a group generate signal. This is a group generate signal from the group of the bitwise ith to kth bit. This is group generate signal from k minus 1 to j bit, This is the propagate, which is a group propagate signal from ith bit to kth bit, right? So similarly, we can also define if j is equal to 0 and I is equal to n minus 1, it will be nothing but n minus 1, and then k will be a bit which is in between n minus 1 to 0. So if I consider that, then p will be n minus 1 is to k, and then jk minus 1 is to 0. Right, so and then the sum of the nth bit will be nothing but the propagate bit level of the nth bit XOR with that of the g n minus 1 is to 0.